Bismillahirrahmanirrahim. This lecture is a continuation of the lectures that I have already sent to you, the part 1, part 2, part 3 on mechanical spring, where we have discussed how to design a spring, what are the spring materials, what are the spring parameters, and all those issues which are related to the design of a spring. Now here what I'm going to focus is on the exercise which is on the design of a spring, and I have two basically things. One is design of a spring under static load and design of a spring under fatigue load. So this particular lecture is about the design of helical compression spring under static load. So we are focusing on the helical compression spring, and the loading nature is static load. And what do we mean by design of a spring? Before we start solving the design problem, so when we talk about the design problem, we are designing a spring. And when we design a spring, what we need to start with? We need to start with wire diameter, which is D. This is the diameter of the wire that the manufacturer will use to manufacture the spring. But with this one, what we are going to get? From the value of the D, we will be able to calculate the S ultimate. We will be able to calculate the yield strength in shear. We will be able to calculate ultimate strength in shear. We should be able to determine what is the E of the material. We should be able to know what is the G of the material. Once we know these, then the spring parameters that we need to find out to complete the design process, we need to have the spring index, we need to have the mean coil diameter, the outer diameter, the inner diameter, the length of the free length of the spring, the shut length of the spring, the total number of coils, number of active coils. We need to determine the torsional stress, and then we need to determine the factor of safety, and we need to also determine the factor of safety against shut, which is the factor of safety at closure. If we know this, we have completed the design of the spring. We need additionally to determine the critical length of the spring, and we need to compare this with LO, the free length of the spring, so that we can determine about buckling. We need to also determine the frequency, the fundamental frequency, so that we can determine what will be the applied frequency. And the applied frequency is the fundamental frequency divided by 15 to 20. Better to use the parameter 20. Just to recap quickly also about the spring, what you call type, you know that we have the spring. This is a helical compression spring which is under a compressive load. And if I draw the cross section of this spring, the top view, then I will see that this is where it will look. This one is the wire diameter, and from the middle, this is the mean coil diameter, and then from the outer we will have the outer diameter, and similarly we can get the inner diameter. Now the example. So first question, this is question number 1, the first example. It says design a helical compression spring under static load. And I have taken this problem from the book so that you can follow it, but please be careful. There are parameters which are given in the book which are not correct. They have a mix of units in the solution of the problem. The spring has to be made from a music wire, and music wire has the designation ASTM A228 if I am correct. The load that will act on this working load is 89, and the working deflection is 50.8 millimeter. Here constraints are defined. What is the first constraint? The solid height cannot be greater than 25. So it means my LS has to be less than 25.4 millimeter. And the free length L0 cannot be more than 101.6. So it has to be less than 101.6 millimeter. So these are my design. This gives me the design constants. So here are my design constants. Okay. Now let's see how we'll. Now we will basically look at it, the parameters again. So the parameters that we have is the force, which is 89 Newton. I have the working deflection of 50.8 millimeter. The length or the shut length is 25.4 millimeter, and the free length is 101.6 millimeter. And as you know that I have told you that in previous slide that the music wire is ASTM228, and that you can see over here right in this one, that this one is the music wire. The number is A228, and this is what we have to use it, and we go to the table. This one is the table 10.4. And what we need from this table, this is the formula that we know. to calculate the ultimate tensile strength. I need A and I need M and I need D, 3 parameters. From here you can see that this is the value of M, and then you can go to the SI unit and you will see this is the value for A. So I know the value of A, I know the value of M. The question of D still remains unknown. I will come to that one in a short while. I will just go to this table, which is the table 10.5. And you can see for a music wire, this is not a complete table. I have just taken only a part of the table. You can, for the music wire, this is the value of E and this is the value of G. So I will pick from here, but it depends on what? It depends on the wire diameter. So in other words, I need to select a wire diameter, and that's the prime variable. So my prime variable for selection in this design exercise is D, which is the spring wire diameter. That's my primary variable. Now here I have selected a diameter of 0.08 inch, which is, I converted into millimeter, which is 2.03 millimeter. This selection is based on a gauge 30 wire and on this ASTM. How we will basically do it? We go to the, this is selected from table A28, and we will do all the calculations based on this design decision, and later we will see whether the design is acceptable or it is not acceptable. So here I put the table, which is not in your notes. It is here, I have added it. You can see this is the gauge. This one column defines the gauge. And this is the music wire. So this is the music wire diameter. And I have selected 30. So if I go in 30 on this one, and I get this. So my D is 0.08 inch. And I need to convert into millimeter. So I will multiply it by 25.4 and I will get 2.032, and I'm going to approximate it as 2.03 millimeter. Somewhere, if the music wire is not clearly specified and you have to use a wire, use this one in your problem, steel wire. But in this table, the value is only given in inches. You need to convert it into millimeter if you are solving in SI unit. If you are solving in FPS unit, then you don't have a problem. Now let's go this. So I know now the D, so I got my ultimate tensile strength. Now once we have the ultimate tensile strength, I need the other material parameter, which we call as SYS, or somewhere it is written as SSY, which is the same thing. or SUS or SSU. This is for static and this is for fatigue load. What is this? This one over here, this Y over here is for yield and this is for shear. So this is the yield strength in shear. How we will get it? We will get it from table 10.6. This is table 10.6. You can see over here, this is the music wire. And I have two conditions. Before set removed and after set removed. This manufacturing process is expensive, but it removes the residual stresses in the spring. So what it does, it removes the residual stresses in the spring after the manufacture. Now what this point 45 means? It means your SYS, right, is equal to 0.45 of S ultimate. This one means your SYS is equal to 0.6 of S ultimate or 0.7 of S ultimate or any value in between. Since this is cheap and it is before set removed, that's what I am assuming in this problem. So before set removed, it will be cheap and we will use that one. So now I got what we call the yield strength in shear. So with this one, I know now three things. I know what is S ultimate. I know what is SY. I also know what is E from previous. I also know G and I also know the wire diameter. So material properties are done. We go to the next on the next slide where I will be selecting. You can see the value of the G and the value of the E. And remember, these values are taken from table 10.5 and they belongs to a certain diameter. And in our case, the diameter that we have is 0.08 inch or 2.03 millimeter. But the table actually uses this value. Now the other one is that in the lecture we have that we have to use the value of C. That's one of the conditions that we have put. Number of active coils, shut factor of safety, and the low robust linearity. And in this case, I'm going to use two of them right now over here. The robust linearity, I'm going to assume 1.2. The condition that we set in the theoretical part is should be greater than equal to 1.2. Robust linearity, I'm going to use 0.15. The condition that we put in the theoretical part of the lecture that it should be greater than 0.15. Now I can use basically, I need to go and first calculate C. So this is assumed, and I'm going to calculate C. And this C is, I'm going to calculate from here. You see this one. Okay. And this C consists of, or calculated using alpha and beta. Alpha, all these values are known. Beta, all these values are known. So I got alpha, I got beta. When I substitute in C, I got C as 10.5. So I got, in other words, I got 10.5 coil, the spring index. Once I know the spring index, I can calculate the mean diameter, which is the spring index multiplied by the wire diameter, which comes out as 21.3 mm. And you can see from here that these is calculated also. We'll go now to calculate these. You see that first we calculated the Berge-Strasser factor, which comes out 1.128 based on the value of C. Let me just remind you over here that this Berge-Strasser factor, I have few choices. I can use Ks, which is called shear correction factor. I can use Kw, which is the wall factor. In this problem, I'm using this. You can use all any three of them, and it depends on the experience of the designer that what correction factor he uses. But in the next problem, I'm going to use the Ks, and you will notice it. So once Kb is known, this already is 0.15. This is given 0.89. This one is 21.3 mm that we calculated. This is the wire diameter 2.03. I got my shear stress, torsional shear stress. Now I can calculate I have this one is the yield strength in shear, and this is the torsional stress. My factor of safety is 1.2, which means it is acceptable. We go further and we say let's calculate OD, which is 21.3 plus this one. If I want to calculate ID, the inner diameter, this is nothing but the mean coil diameter minus T. The next is to calculate active coils, which is here. Do I note this is the equation that you can see, the same equation. G is known, D is known, maximum deflection is known, maximum force, mean coil diameter. When I substitute all of these, it comes as 10.16 coil. And we assume squared and ground end, and we got 12.6 as the total coil. Once the total coil is known, then I know that length at the shut is D times N times of NT, total number of coils. And that's what you did. This is the diameter of the wire, and this is the total number of coils. So this is the shut length. And the free length is given by this. You can actually use it. I think the value is given in one of the table, which is the table 1. This is given in table 1. And I will use another way to calculate it in the next problem. Once I know this, all of this, what two things is left is the critical length, which is equal to 2.63 times the mean coil diameter divided by alpha, and alpha is dependent on the end condition. So we are saying fixed ends parallel, value of alpha is 0.5. We put it, we got this. Now notice L0 must be less than critical, so that no buckling. This is 83.1 and this is 112. So it means it is fine. There will be no buckling. This is the figure of merit. You can calculate it by using this equation, but I just want to show you only the calculation, and I'm not going to stick with it right now. All of these parameters you know, except the relative material cost. You see over here the relative material cost is 2.6. That I have used it over here, and the rest, and we calculate this one. We'll use it when we have to make a decision between few choices, all of them acceptable, and we will do them by comparison of cost. So here what you have seen, that we have designed this, right? we calculated the mean coil diameter, spring index, outer diameter, active coil, shut length, free length, critical length, and the factor of safety at shut. I can also put over here the ID. And then we will check that whether it is acceptable or not. My condition to accept is one, that active coil has to satisfy this, a spring index has to satisfy this, factor of safety at shut has to be this, length has to be, free length has to be less than critical, and these are the two design constraints which are given. That free length has to be less than this and solid length has to be less than this. Now, how do you know that this is the best wire? So what we need to do, we need to do this exercise to generate a design map. This is a design map. For all possible diameters, not all, means that you think which is acceptable, which is in the range. Sometimes what happens, a company has 7 different types of wires. So you need to check with all the 7 different types of wires. So here, if I just go and I say, okay, let me, I just want to erase this line. So I will erase it and I will go back to the pen. So now I'm going to repeat the whole calculation use for 1.6 mm diameter, 1.7, 1.8, 1.9, 2.1 and 2.3 and 2.4. This we have done it. It is better to put all these formulas that we have used, which are very simple, small formulas, in Excel software as a function of wire diameter. So the moment you change the wire diameter, you'll get the whole column. And this is the column that you will get when you use all these different wires. So I have a design map and I have to make a decision. So my first decision is, let me check this, the active coil. This is, so I will go and I will say, okay, now I'm going to delete, which are not acceptable. This is not, because it is greater than 15. This is not. This is also greater than 15. This is acceptable. So when I see this is, all these lines are acceptable. We go to the second one, which is the spring index. Is that acceptable? Yes. It has to be greater than 4 and less than 12. So this is fine, this is fine, fine, fine. This is 12. This is the limit. Okay, this is greater than 12. So this is not, this is not. This is already out. Now we'll go to the given condition. My shut length, it has to be this, right? Less than 25.4. Is that? No. Out. This is out. This is out. This is out. And now these 4, you can see they are fine. And the free length has to be less than 101.6. So I go back and check it. This is unacceptable. This is unacceptable. This is okay. Let me erase it. I have to go and I have to erase this one. Okay. Now if you look at from this, you can see that is this column? No, unacceptable, because there are so many violations. This design, unacceptable. This design is unacceptable. This design is unacceptable. This design is unacceptable. This design is unacceptable. So I am left with only two choices. I'm left with one is this choice and one is this choice. So what I will look at it in these two. And let me look at the value of the C. Here what is the value of the C? 10.5, and here it is 12. Which one is better? Definitely the one which is within this range, because 12 is at the boundary. So I will discard this one. So what is my design? My design is this one. And this is what you will see. I have put it over here. And these are my all design parameters. Wire diameter, spring index, mean coil diameter, outer diameter, inner diameter, number of active coils, total number of coils, what is the end condition, what is the factor of safety at shut, what is the free length, and what is the shut length, that a spring will not buckle. Another thing that you have noticed in this one is if you look at these two, compare between these two values. Here the critical length is less than the free length, so it's unacceptable, right? Here is also the same thing. Here is also the same thing. Here it is fine. Here it is fine. I forgot to mention on this one. So that completes the first problem. Let me go to the second. Now this is the second problem where I need to design a helical compression spring that will work with the minimum load of this and maximum load of this, and the working deflection is this. Now what does it mean? So I will just draw a spring and I'll say, okay, here is the spring and here is the load, and I call this as the minimum load. And then what happened, the spring goes to this, here is the maximum load. This is 150 pound and this is equal to 100 pound. And when this is done, the spring has deflected. That deflection is 0.75 inch. So in other words, I can directly find K, spring rate, which is 150 minus 100 divided by 0.75. Now let's start the problem. Here the wire material is not specified. Is not specified. So what we will do? We will assume. And what we will assume? The least expensive So we took the least expensive cold drawn spring wire, which is A227. We go to the table 10.4. We found A is this, M is this. Now I need to find out what is the D, so that I can calculate the ultimate tensile strength. So I go to the table 828 and I have selected gauge 20 intentionally. Otherwise, you will have to start from somewhere. And it's a trial. You will go basically and then you will improve your design. What is the diameter that we got? 0.161. So I put this in the formula and I got S ultimate as 198 SI. Now this time I'm going to use the material as a after set removed. This is more expensive than before set removed. And you remember the value that we had between 0.6 to 0.7, and I've chosen the lower value of this. So I got what is my yield strength. This is not US, this is the shear yield strength. And again I go back to the table 10.5 and I found what is E and what is G. So what is known now? Diameter of the wire, ultimate tensile strength, and this is not correct. This is the yield strength in shear, E and G. Now where to start now? Here this time I'm not going to use the table. The table or the, not the table. Let me delete this. I'm not talking about the table, but I will just say the figure that we have used, and that figure is, if I am not mistaken, it is figure 10.3. Figure 10.3. It follows a process. I'm not going to use this. I will follow a different approach. So I'm going to use a different approach. And this is another way. I know that the C has to be between 4 and 12. So I will assume C as 8. So you see over here, I have made two assumptions now. I have assumed the wire diameter, this is 1, and I have assumed the spring index, which is 2. Once the spring index is known, I can find out what is the mean coil diameter. And I go to the equation which is tau S is equal to K S 8 F D divided by pi d cube. And I'm going to use here the maximum force, F maximum, so that C is not used. Now instead of this case, you can also use KB or KW, but to just change the flavor. So this is the KS, we got 1.06. I know the F maximum 150. I know D, which is this one, 1.29. And the wire diameter I have already assumed. I got this one. The shear stress is 125.16. Can I calculate factor of safety? Yes, because I know the yield shear strength. I know this. This is my factor of safety, which means the design is unacceptable. What I want to do, I need to now increase the wire diameter. So I go and I say, let me use the gauge 10. The diameter is this. I calculated D again. I calculated tau again. And I calculated S ultimate again. I calculated the yield strength again. I calculated the factor of safety now, 1.29, which means that this is acceptable. Once this is acceptable, now I will go and find out all the parameters. So first, I showed you on the first slide, the K is this. So we calculated K. Once we know the K, I can use this equation. K is known, wire diameter is known, G is known, mean coil diameter is known. I can find out NA. Now here, if you notice, I have rounded it up. This rounding is done like this. I will choose this 0.00, 0.25, 0.50 and 0.75. So whatever be the value comes, I will see which decimal place it is closer to, and I will choose that one. So let's look at 7.94. The 7.94 is close to 8 because 7.94 will be between 7.75 and 8.00, where it is close to this one. So I have chosen this. If it will be close to this one, I will be choosing this one. But here it is. So if my coil has changed, it means the K will change again, and that's what I did. Before the K was, before what was K? Before K was 66.7. Now it has changed to 66.2. So once the coils are known, I assume the end condition. I know what is the total number of coils. I can find out what is the shunt length. I can find out what is the initial deflection here. And that's very interesting because I take a spring, I apply an initial load, which is how much here? 100. Then I apply a maximum load, so it goes to this. And then I have, if you remember in this one, I said a clash allowance to prevent clash. Before it goes to the solid height. Okay. So I know the initial deflection. I know the working deflection, which is 0.75, that I already know. And I can calculate the clash allowance, which is 15%. I have taken. So if I take the initial deflection, working deflection of 0.75, clash allowance is this, solid length is this, I get this is the free length of this spring. Now I need to do two things. I need to check whether this free length is less than the critical length. And the second, I need to find out what is the factor of safety against shunt. So in order to find out the factor of safety of this spring at closure, what I need to find out, how much is the deflection. So the deflection is free length minus shunt length. That's the deflection it has to go in order to put it in a shut condition. It means if I multiply this by K, I will know what is my shut force. So this is my shut force. Once I have the shut force, I can calculate shut stress. This is my shut stress. I already know my yield strength in shear. I know my shut stress. I check basically the value of the shut factor of safety, which is 1.24. It is greater than 1.2. So it is acceptable. You remember what we got? NA is equal to 8 coils. Again, it is between 3 and 15. So acceptable. You know the C is equal to 8, which is again between 4 and 12. So it is also acceptable. Here we don't have to create a design map because we are checking everything in between. Since all the things are acceptable, I can calculate ID and I can calculate OD, and I know all these conditions are satisfied. The last thing, I calculate the critical length. Critical length comes 8.05. Remember what was my free length? 4.28. What is my critical length? 8.05, which is free length is less than that, so there will be no buckling. So when I write now design parameter, I will say D is 0.191 inch, C is 8, active coils is also, if I think what I remember, we got 8 coils, right? Yeah, active coils is 8, total number of coils is 10, and is squared and ground. Right. Material is ASTM A227. OD is 1.339 inch. ID, sorry, this is not 1.3. OD is, let me erase it. Okay, so I'll go back. The OD is 1.721 and ID is 1.339 and D is 1.3. Factor of safety against shut is 1.24 and the factor of safety of the spring is 1.29. Right? Do we have all the parameters? I think so. We have the mean coil diameter, spring index, outer diameter, active coil, shut length. We can also write what is the shut length of the spring, and the shut length came is how much it came, the shut length. The, let me see, is what is my, the shut length came as 1.91. So all these are all inches. With this we complete the 2 examples on the design of springs under static load conditions, and I will finish my lecture over here, and I will see you soon with the dynamic load examples. Have a good day.